Welcome to this session on correlation analysis. In correlation analysis, today we want to look at the concept of correlation in terms of description or definition. And we also want to look at the various types of correlation. And finally, we shall look at one of the coefficients of determining correlation between two variables by Pearson. And then maybe later on in another session, we shall discuss the Spearman rank correlation coefficients. Those are the two common correlation coefficients that are used in determining the correlation or establishing the relationship between variables. Now, correlation is defined as a measure of how two or more variables are related. So whenever we say two variables are related or two variables have an association between them in statistics, then the measure that we are talking about is correlation. And so that association, if we can be able to quantify it and know the direction, then we are actually describing correlation. So correlation measures strength and direction. So those are the two aspects that we seek to establish whenever we are talking of an association or a relationship existing between two variables. And therefore, this relationship between two variables, when you quantify it, it will always range between -1 to +1. So that's the scale of correlation. So it always lies between +1 and -1. Actually, at these endpoints at -1 and +1, we talk of perfect correlations. So we can have perfect strong positive correlation and perfect strong negative correlation of -1. But of course, in reality, whenever you have data and you are establishing the correlation between the variables, you'll hardly find such kind of values. And so you'll always find correlation coefficients of values that are either approaching +1 or approaching -1 or values around 0, so on. And so whenever you get values around -1, let's say -0.96, -0.8, even -0.75, then we describe that kind of relationship between the variables as a relationship of strong negative correlation. Whenever we have values of the correlation, values approaching -1. In the same manner, when you get the correlation coefficients of values of, let's say, +0.7 something all the way to +1, then we talk of the relationship between the two variables having a strong positive correlation. Sometimes we get now values around, let's say, +0.5, the midpoint of 0 and 1, or +0.55, +0.57, +0.479, values around +0.5. So in this case, the adjective we use to describe that kind of correlation is moderate. You talk of the relationship between the variables being a moderate positive correlation. And if it is actually a negative, you now talk of a moderate negative correlation between the variables. And of course, values that are values of correlation around 0, whether you are talking of 0.2 or -0.2, -0.1, here we normally use the term weak. We talk of weak correlation existing between the two variables. So it can be a weak positive or a weak negative, depending with the direction or the sign of the correlation coefficient you have found. So that from this, then we classify correlation basically into 3 categories. So that we say correlation can either be positive, correlation can either be negative, or we can actually have 0 correlation or no correlation at all. And you can see the scatter plots when you have positive correlation between the variables. you can see if I'm to plot a baseline of it, you find that this line will have a positive gradient, a straight line with a positive gradient. Then these two variables are said to have a positive correlation. And a good example in this case could be, you are looking at, let's say, this could be weight, and this could be, let's say, the height of maybe children under 10 years. When kids are born, particularly in the period of 0 to 10, you'll find as the kid increases in height, the weight of the kid also increases. So the two variables are positively correlated. You can also talk of maybe, let's say, income and expenditure. Yes, people earn more tend to also spend more. And so those kind of variables have a positive correlation. Then we can also have negative correlation where you can see the trend now is a reverse. An increase in one variable automatically leads to a decrease in the other. And this could be, maybe a good example could be the price of a commodity, and maybe this is the demand of the quantity. So you can see the price is low when the quantity is actually, of demand is high. So that's a good example of two variables that are actually negatively correlated. Then you can have something like zero correlation here. You can be talking of maybe you could talk of maybe even this could be even education, and maybe this is marital status, and maybe you're talking of have no kind of relationship. You can see there is no a demonstrated connection. You can't draw a baseline of it. So here you're looking at it like we can't say there is a linear kind of relationship. And by the way, the correlation we are discussing here, we are assuming mostly linear relationship, but it is possible that you can also have a correlation between variables that is actually non-linear. You can actually have a correlation between variables, y and x, and you find that this relationship is not linear, but is actually non-linear. That is also possible. You can have even a curve like this, so that now you have data all through. So in such a scenario, we talk of a non-linear relationship, although that is not the essence of our discussion today. Today we are assuming that actually the relationship that exists is linear. So once we have drawn the scatter plot and assumed that or concluded that a relationship between the variables we are discussing is linear, we now come to the very common coefficient that is used to actually now help us determine the strength of the relationship by giving us a numerical figure. And this is called Pearson correlation coefficient, denoted by R. By definition, of course, correlation is given by covariance divided by the square root of the product of the variances of the individual variables. So this is actually the definitional formula. But for purposes of computation and in classwork, you'll find that that definition formula sometimes is a bit cumbersome and tedious to use. And you'll find it easier to compute using the equivalent computational formula given by this, which I always prefer to actually break it down so that this numerator component, we just denote it as SXY, and these ones we denote them as SXX, SYY, so that if we compute them separately before we now plug them in the formula, it becomes easier for us. So let's begin by now looking at an example that makes use of this formula so that we see how we can actually compute the correlation. So if we have data here of students who have sat for a contest, and they have maths and English, and there are 10 of them, and we have those kind of results. So suppose we want to establish the correlation between the performance in maths and English. So you need to, first of all, decode the maths, do the coding, so that maths and English, one can be X, another one Y. You can see the formula for Pearson correlation coefficient is having only X and Y. It doesn't have the maths and English. So that means you have to really now also assign, let this variable maths maybe be called X, then English now you be represented by Y, so that then now you can still go ahead now to use the formula. Now, when you look at the formula, it requires that we need to have, first of all, the product of X and Y. We need summation of X, summation of Y, summation of X squared, summation of Y squared. So this actually, in a way, gives you a hint of the kind of columns you need to create. So you can now rewrite this table in vertical format, like in this case, now with maths being represented by X, English as Y, so that now you are adding now some 3 more columns where you're now having X squared, Y squared, and XY, because those are the components we need. So that down here, to now be getting summation X, when I sum that column of X, I'll also sum the column of Y. I'll also get now sum of X squared, sum of Y squared, and sum of XY. With those components obtained, as they are displayed here, you can see summation of X is 80, summation of Y 200, summation X squared 910, summation of this and this. It becomes easier for us now to calculate the components that can help us now determine the correlation coefficient, like SXY now. We just pick those and plug in, we get 53, SXX, 270, SYY, 250. So with them now, when you plug in the formula, we get a value of 0.204. So 0.204, again, we can see it's a value lying between -1 and +1. But you can see it's a bit closer to 0, much more closer to 0 than the endpoints. So this is an indication of a weak kind of correlation existing between the performance in maths and the performance in English. So you talk of a weak positive correlation in performance of maths and the performance of English. And this could maybe mean that you could not maybe predict the performance of one subject using maybe the performance of the other. But of course, that is subject to another discussion. Now, what then are the assumptions of Carl Pearson? Carl Pearson works on some assumption. Whenever you're using it, it assumes some things. The most common ones that Carl Pearson assumes assumes, first of all, whatever you have mentioned, that first of all, the correlation, the relationship between the variables is linear. I've said when you, first of all, state draw the scatter plot, of course, it will give you the pattern and trend of the relationship between them. And so you can be able to tell whether it is linear or not. And so you make sure that it's linear. Otherwise, if the relationship is not linear, then it means then if you use this Carl Pearson, the value will get maybe unreliable. It also assumes that the variables, first of all, are continuous and data interval or ratio scales, and also assumes that there are no outliers in the data sets across the variables. So those extreme values can actually alter the reliability and the accuracy of the value. And it also makes a strong assumption that the data follows normally distributed, that each of those variables are normally distributed. And so it is this strong distribution assumption that makes Carl Pearson correlation coefficient to be called sometimes as a parametric test statistics. When we mention the list of test statistics are parametric, Carl Pearson comes in handy. So this is the most common correlation coefficient that is used in correlation. Remember, correlation is one of the descriptive analysis tools that is used mostly in statistics whenever people are doing analysis. Before, as one of the very, very precursor stage before you carry out maybe serious analysis like regression analysis, multivariate analysis. and even machine learning, and predictive modeling. And so it is an important concept that we really need to understand. And so in case when these assumptions are violated, then we always resort to a Spearman rank correlation coefficient that we shall discuss in another video. Thank you so much.